A klystron is a specialized linear beam vacuum tube, invented in 1937 by American electrical engineers Russell and Sigurd Varian, which is used as an amplifier for high radio frequencies, from UHF up into the microwave range. Low-power klystrons are used as oscillators in terrestrial microwave relay communications links, while high-power klystrons are used as output tubes in the UHF television transmitters, satellite communication, and radar transmitters, and to generate the drive power for modern particle accelerators. In the klystron, an electron beam interacts with the radio waves as it passes through resonant cavities, metal boxes along the length of the tube. The electron beam first passes through a cavity to which the input signal is applied. The energy of the electron beam amplifies the signal, and the amplified signal is taken from a cavity at the other end of the tube. The output signal can be coupled back into the input cavity to make an electronic oscillator to generate radio waves. The gain of klystrons can be high, 60 decibels or more, with output power up to tens of megawatts, but the bandwidth is narrow, usually a few percent, although it can be up to 10% in some devices. A reflex klystron is an obsolete type in which the electron beam was reflected back along its path by a high-potential electrode, used as an oscillator. The name klystron comes from the stem form kappa lambda upsilon sigma of a Greek verb referring to the action of waves breaking against a shore, and the suffix tau rho o micron nu meaning the place where the action happens. The name klystron was suggested by Hermann Fraenkel, a professor in the classics department at Stanford University when the klystron was under development. History. The klystron was the first significantly powerful source of radio waves in the microwave range. Before its invention, the only sources were the Barkhausen-Kurz tube and split anode magnetron, which were limited to very low power. The klystron was invented by the brothers Russell and Sigurd Varian at Stanford University. Their prototype was completed and demonstrated successfully on August 30, 1937. Upon publication in 1939, news of the klystron immediately influenced the work of US and UK researchers working on radar equipment. The Varians went on to found Varian Associates to commercialize the technology. Their work built on the description of velocity modulation by A. Arsenjoa Heil and Oscar Heil in 1935, though the Varians were probably unaware of the Heil's work. The work of physicist W.W. Hansen was instrumental in the development of the klystron. It was cited by the Varian brothers in their 1939 paper. His resonator analysis, which dealt with the problem of accelerating electrons toward a target, could be used just as well to decelerate electrons. During the Second World War, Hansen lectured at the MIT Radiation Labs 2 days a week, commuting to Boston from Sperry Gyroscope Company on Long Island. His resonator was called a rumbatron by the Varian brothers. Hansen died of beryllium disease in 1949 as a result of exposure to beryllium oxide. During the Second World War, the Axis powers relied mostly on klystron technology for their radar system microwave generation, while the Allies used the far more powerful but frequency-drifting technology of the cavity magnetron for much shorter wavelength 1 cm microwave generation. Klystron tube technologies for very high-power applications, such as synchrotrons and radar systems, have since been developed. Right after WW2, AT&T used 4-watt klystrons in its brand-new network of microwave links that covered the U.S. continent. The network provided long-distance telephone service and also carried television signals for the major TV networks. Western Union Telegraph Company also built point-to-point microwave communication links using intermediate repeater stations at about 40-mile intervals at that time, using 2K25 reflex klystrons in both the transmitters and receivers. How it works. Klystrons amplify RF signals by converting the kinetic energy in a DC electron beam into radio frequency power. A beam of electrons is produced by a thermionic cathode, and accelerated by high-voltage electrodes. This beam is then passed through an input cavity resonator. RF energy is fed into the input cavity at or near its resonant frequency, creating standing waves, which produce an oscillating voltage which acts on the electron beam. The electric field causes the electrons to bunch. Electrons that pass through when the electric field opposes their motion are slowed, while electrons which pass through when the electric field is in the same direction are accelerated, causing the previously continuous electron beam to form bunches at the input frequency. To reinforce the bunching, a klystron may contain additional buncher cavities. The beam then passes through a drift tube in which the faster electrons catch up to the slower ones, creating the bunches. Then through a catcher cavity. In the output catcher cavity, each bunch enters the cavity at the time in the cycle when the electric field opposes the electrons' motion, decelerating them. Thus the kinetic energy of the electrons is converted to potential energy of the field, increasing the amplitude of the oscillations. The oscillations excited in the catcher cavity are coupled out through a coaxial cable or waveguide. The spent electron beam, with reduced energy, is captured by a collector electrode. To make an oscillator, the output cavity can be coupled to the input cavity with a coaxial cable or waveguide. Positive feedback excites spontaneous oscillations at the resonant frequency of the cavities. Two-cavity klystron. The simplest klystron tube is the two-cavity klystron. In this tube there are two microwave cavity resonators, the catcher and the buncher. When used as an amplifier, the weak microwave signal to be amplified is applied to the buncher cavity through a coaxial cable or waveguide, and the amplified signal is extracted from the catcher cavity. At one end of the tube is the hot cathode heated by a filament which produces electrons. The electrons are attracted to and pass through an anode cylinder at a high positive potential. The cathode and anode act as an electron gun to produce a high-velocity stream of electrons. An external electromagnetic winding creates a longitudinal magnetic field along the beam axis which prevents the beam from spreading. The beam first passes through the buncher cavity resonator, through grids attached to each side. The buncher grids have an oscillating AC potential across them, produced by standing wave oscillations within the cavity, excited by the input signal at the cavity's resonant frequency applied by a coaxial cable or waveguide. The direction of the field between the grids changes twice per cycle of the input signal. Electrons entering when the entrance grid is negative and the exit grid is positive encounter an electric field in the same direction as their motion, and are accelerated by the field. Electrons entering a half cycle later, when the polarity is opposite, encounter an electric field which opposes their motion, and are decelerated. Beyond the buncher grids is a space called the drift space. Its length is chosen to allow maximum bunching at the resonant frequency, and may be several feet long. The electrons then pass through a second cavity, called the catcher, through a similar pair of grids on each side of the cavity. The function of the catcher grids is to absorb energy from the electron beam. The bunches of electrons passing through excite standing waves in the cavity, which has the same resonant frequency as the buncher cavity. Each bunch of electrons passes between the grids at a point in the cycle when the exit grid is negative with respect to the entrance grid. So the electric field in the cavity between the grids opposes the electron's motion. The electrons thus do work on the electric field, and are decelerated. The kinetic energy is converted to electric potential energy, increasing the amplitude of the oscillating electric field in the cavity. Thus the oscillating field in the catcher cavity is an amplified copy of the signal applied to the buncher cavity. The amplified signal is extracted from the catcher cavity through a coaxial cable or waveguide. After passing through the catcher and giving up its energy, the lower energy electron beam is absorbed by collector electrode, a second anode which is kept at a small positive voltage. Klystron oscillator. An electronic oscillator can be made from a klystron tube by providing a feedback path from output to input by connecting the catcher and buncher cavities with a coaxial cable or waveguide. When the device is turned on, electronic noise in the cavity is amplified by the tube and fed back from the output catcher to the buncher cavity to be amplified again. Because of the high Q of the cavities, the signal quickly becomes a sine wave at the resonant frequency of the cavities. Multi-cavity klystron. In all modern klystrons, the number of cavities exceeds 2. Additional buncher cavities added between the first buncher and the catcher may be used to increase the gain of the klystron, or to increase the bandwidth. The residual kinetic energy in the electron beam when it hits the collector electrode represents wasted energy, which is dissipated as heat, which must be removed by a cooling system. Some modern klystrons include depressed collectors, which recover energy from the beam before collecting the electrons, increasing efficiency. Multi-stage depressed collectors enhance the energy recovery by sorting the electrons in energy bins. Reflex klystron. The reflex klystron was a low-power klystron tube with a single cavity, which functioned as an oscillator. It was used as a local oscillator in some radar receivers and a modulator in microwave transmitters the 1950s and 60s, but is now obsolete, replaced by semiconductor microwave devices. In the reflex klystron, the electron beam passes through a single resonant cavity. The electrons are fired into one end of the tube by an electron gun. After passing through the resonant cavity, they are reflected by a negatively charged reflector electrode for another pass through the cavity, where they are then collected. The electron beam is velocity modulated when it first passes through the cavity. The formation of electron bunches takes place in the drift space between the reflector and the cavity. The voltage on the reflector must be adjusted so that the bunching is at a maximum as the electron beam re-enters the resonant cavity, thus ensuring a maximum of energy is transferred from the electron beam to the RF oscillations in the cavity. The reflector voltage may be varied slightly from the optimum value, which results in some loss of output power, but also in a variation in frequency. This effect is used to good advantage for automatic frequency control in receivers, and in frequency modulation for transmitters. The level of modulation applied for transmission is small enough that the power output essentially remains constant. At regions far from the optimum voltage, no oscillations are obtained at all. There are often several regions of reflector voltage where the reflex klystron will oscillate. These are referred to as modes. The electronic tuning range of the reflex klystron is usually referred to as the variation in frequency between half power points, the points in the oscillating mode where the power output is half the maximum output in the mode. Modern semiconductor technology has effectively replaced the reflex klystron in most applications. Tuning. Some klystrons have cavities that are tunable. By adjusting the frequency of individual cavities, the technician can change the operating frequency, gain, output power, or bandwidth of the amplifier. No two klystrons are exactly identical. Each unit has manufacturer-supplied calibration values for its specific performance characteristics. Without this information, the klystron would not be tunable properly, and hence not perform well, if at all. Tuning a klystron is delicate work which, if not done properly, can cause damage to equipment or injury to the technician due to the very high voltages that could be produced. The technician must be careful not to exceed the limits of the graduations, or damages to the klystron can result. Other precautions taken when tuning a klystron include using non-ferrous tools. Some klystrons employ permanent magnets. If a technician uses ferrous tools and comes too close to the intense magnetic fields that contain the electron beam, Such a tool can be pulled into the unit by the intense magnetic force, smashing fingers, injuring the technician, or damaging the unit. Special lightweight non-magnetic tools made of beryllium alloy have been used for tuning U.S. Air Force klystrons. Precautions are routinely taken when transporting klystron devices in aircraft, as the intense magnetic field can interfere with magnetic navigation equipment. Special overpacks are designed to help limit this field in the field, and thus allow such devices to be transported safely. Optical klystron. The technique of amplification used in the klystron is also being applied experimentally at optical frequencies in a type of laser called the free electron laser. These devices are called optical klystrons. Instead of microwave cavities, these use devices called undulators. The electron beam passes through an undulator, in which a laser light beam causes bunching of the electrons. Then the beam passes through a second undulator, in which the electron bunches cause oscillation to create a second, more powerful light beam. Floating drift tube klystron. The floating drift tube klystron has a single cylindrical chamber containing an electrically isolated central tube. Electrically, this is similar to the two-cavity oscillator klystron with a lot of feedback between the two cavities. Electrons exiting the source cavity are velocity modulated by the electric field as they travel through the drift tube and emerge at the destination chamber in bunches, delivering power to the oscillation in the cavity. This type of oscillator klystron has an advantage over the two-cavity klystron on which it is based. It only needs one tuning element to affect changes in frequency. The drift tube is electrically insulated from the cavity walls, and DC bias is applied separately. The DC bias on the drift tube may be adjusted to alter the transit time through it, thus allowing some electronic tuning of the oscillating frequency. The amount of tuning in this manner is not large and is normally used for frequency modulation when transmitting. Applications. Klystrons can produce far higher microwave power outputs than solid-state microwave devices such as gun diodes. In modern systems, they are used from UHF up through hundreds of GHz. Klystrons can be found at work in radar, satellite and wideband high-power communication, medicine, and high-energy physics. At SLAC, for example, klystrons are routinely employed which have outputs in the range of 50 megawatts and 50 kilowatts at 2856 megahertz. The Arecibo planetary radar uses two klystrons that provide a total power output of 1 megawatt at 2380 megahertz. Popular Science's Best of What's New 2007 described a company, Global Resource Corporation, currently defunct,